Hi everyone, I'm Jamie from Chegg Tutors. Today I want to talk to you about something in set theory, the relationship between equivalence relations and partitions of a set. So equivalence relation is a relation that is reflexive. In other words, x is related to x. It's symmetric. In other words, if x is related to y, y is related to x. And it's transitive. If x is related to y and y is related to z, then x is related to z. Now, the simplest example of an equivalence relation on any set is simply equality. X is equal to x. If x is equal to y, y is definitely equal to x. And if x is equal to y and y is equal to z, x is equal to z. This works on any set that includes numbers. But this is a much more general relation. You could take the set of names of fruits and define an equivalence relation on them based on, say, color. Two objects, two fruits are in the same equivalence class, or they're related to each other if they're the same color. So is a banana related to a banana? Yes, they're both yellow. If a banana is related to a pineapple, is a pineapple related to a banana? Sure, this means they have one color, this means they have the same color. Is an apple related to a tomato? Yes. And if a tomato is related to a pomegranate, then that means that these both mean that the fruit is the same color, the color red. So the apple is going to be the same color as the pomegranate. That's kind of a stupid example, but it just goes to show that equivalence relations can be more than just equality and work with more than just numbers or functions, the kinds of things we're used to in math. So this is really the power of set theory, that we can define these very, very general things and find results about that, like we will here. A more concrete example of an equivalence relation. Modular arithmetic, any congruence where you say modulo any number, modulo n, here modulo 3, is an equivalence relation on the integers. In other words, and we know that every integer is congruent to either 0, 1, or 2 mod 3. That's simply another way of saying that if you divide an integer by 3, you're either going to get a remainder of 0, if it's a multiple of 3, you're going to get a remainder of 1 or a remainder of 2. Because if you keep going, say if you get a remainder of 3, well, that's actually a remainder of 0 because it's another multiple of 3. If we were to write this out, you could say that 1 is equal to 4 mod 3. If you add 3, that's equal to 7 mod 3 is equal to 10 mod 3, etc. Any multiple of 3 is going to be 0 mod 3. Anything that's 2 plus a multiple of 3 is going to have modulo 3 is going to be 2. We also notice that no integer has two different remainders when divided by 3. In other words, every integer is going to be exclusively either 0, 1, or 2 mod 3. Also, it can't be 0 and 1 mod 3. It also has to be one of these things. So 0, 1, and 2, the classes of numbers that fall into these sets, if you take their union, then you're going to get all of the integers. That's another way of saying every integer has some remainder mod 3. That leads us to our idea of how we relate equivalence relations and partitions of a set. Now, a partition of a set is simply a subset or a set of subsets such that the sets are disjoint and the union of all the sets is equal to the whole set X. So a partition of the integers could be the set of even integers and the set of odd integers. No integer is both even and odd, and if you take both even and odd integers, you get all integers. Could also be the sets equivalence classes modulo a certain number. So the set 0, 3, 6, etc., and then 1, 4, 7, etc., and then 2, 5, 8, etc. No integer, again, like we said, is equivalent to, has the same modulus, no integer, has two different remainders mod 3 when you divide it by 3. But every integer has some remainder, either 0, 1, or 2, when you divide it by 3. That's an example of how you create a partition from an equivalence relation. A partition comes out of sets, e to the x, defined such that y is in e to the x if y is equivalent to x, if y and x are in the same equivalence class. In other words, if you have two things, so you have say you have a partition into 3 different sets, different equivalence classes, A, B, and C. Now, if this is an equivalence class on a set, we know that it's a relation, so every member of this one of these equivalence classes. Now we have to think about whether A, B, and C have any overlapping members. Well, if there's something that's equivalent, if x is equivalent to y in A, and we also have okay, so if x is equivalent to A, say that the A is the equivalence class of elements related to equivalent to A. X is equivalent to A, and x is equivalent to B. Then A is equivalent to B, which means that A and B are not distinct elements. So these equivalence classes are also going to be disjoint. They're not going to be overlapping. So anything that has disjoint sets that together, taken the union of, forms the whole set is a partition. That's how you get from an equivalence relation to a partition. You can also go the other way around and define an equivalence relation by x being related to y if they're in the same equivalence class. It should be, I'll leave it as an exercise to the viewer to prove that other direction. This is a very general introduction to how we can use and relate equivalence relations and partitions, but that's actually the power of set theory, that you can define very general results and then apply it to any set you want. That's it for now, and see you next time.